Okay, so let's talk about functions, this time for real, all right? Now, functions, you might think to yourself, okay, what in the world are we even going to talk about? Thought we talked about functions all during high school. That's true, but you talked generally about functions of a certain type. You typically would have like a function of a variable x. X would be called like the input, and then you would have the output f of x, right? And so you thought of the function as kind of operating on the input x. And maybe f of x was like x squared or something like that, right? Which means that whatever the input is, you square it. And incidentally there, it kind of goes without saying that your input is a number and that the output is a number. Does that make sense? So most of the functions you've dealt with are functions of x, where x is a number, and then the output itself is also a number. But functions in the more broadly general sense don't have to be numeric in nature at all. You don't even have to have a numerical input, okay? You don't have to have a numerical output. I might have a function that's called like a marriage function, where I line all the ladies up on one side of the room or something like that, and all the guys up on the other side, and I say, the input is this lady, the output is that guy over there. Hope you're happy, right? You could actually have functions from people to people. You could have functions from where the input is a number, but the output is not a number, okay? There's also, like generally speaking, functions can take on all sorts of looks, okay? So we want to talk about functions in that general sense. So the way we're going to be talking about it right now, it's going to feel somewhat kind of like abstract in some ways, but hopefully it'll make sense when we take it down to the level of numerical inputs and whatnot. Okay, so what's a function? Well, now that we have all of our background and sets and whatnot, you start with a couple of non-empty sets. A function f from a to b, and the notation for it is this right here, okay? So f, and you put colon, a arrow b. So that means, by the way, that the input, I'm going to hide names of annotators here. The input always comes from a, so this set a, this is the set of inputs, and the output of the function resides here. So these are the output. These are the potential outputs over here, okay? Is an assignment of each element of A to exactly one element of B. And this is the key, exactly one element of B, okay? What was the requirement in high school that something be a function? You remember, Trey? It has to pass the vertical line test. Yes, vertical line test. What does that have to do with this? Okay, here it says that any input can have, right, basically any input, that is any element from A via the function can go to exactly one element of B. Yes, exactly one. Well, that vertical line test is actually checking that that's the case. Does that make sense? Because if I had something like, f of x equal to x squared, okay, of course, it looks like this, right? And you say to yourself, yeah, that passes the vertical line test. Look, it only hits the function in one place. Well, that is basically kind of like a practical way of checking this condition. Because what you're doing is saying, what about this input right here? What about this x value? How many outputs are there? Well, the outputs are these y values, right? The outputs are the y values on the graph. And you're just making sure that how many outputs are there for that input? One, right? So the vertical line test is making sure that you have exactly one output for each input. Does that make sense? Okay, but we're kind of talking about this more generally than just functions of numbers. Okay. A is often called the domain. of the function? You guys have heard that language before, right? What is the domain of this function? So like f of x equal to x squared. This is a function that takes inputs from where? Real numbers. Remember our newfangled notation for some of these things? Inputs are basically from the real numbers. And where do our outputs live? Real numbers, that's right. Okay. So A, right, and generally speaking, we had a function that was just going from some set A to some set B, which aren't even necessarily numerical. But A is the domain of F. So if I had some kind of restricted domain, so for instance, here's an example. What about f of x equal to the logarithm of x? Okay. What about f of x equal to the logarithm of x? Where does this function go from? So look, I'm saying that A, the set of inputs, that needs to be the domain of the function. So here, would I be permitted to put all real numbers as the domain? No. What would be the domain in this case? Strictly positive numbers, yes? Okay, so for instance, I could write that as like r plus. Okay, so the f would go from r plus to the real numbers. Yeah? Okay, in this particular case. Now, the codomain is a little bit looser. Okay? The codomain is just the kind of collection of things that the outputs live in. Does that make sense? So for instance, f of x equal to x squared, I wrote the codomain. The codomain is the place we go, like where the outputs live. So like in the case of f of x equal to x squared, the codomain I wrote as the real numbers. But is every real number hit by that function? No, in fact, only what sorts of numbers are hit by that function? Yeah, non-negative, right? 0 or any positive number. But I don't ever get any negative numbers. Does that make sense? Okay. Now that is going to be called something else. The stuff that gets hit by the function in the output realm, namely the codomain, that's going to be called the range of the function. Yes? The range is the collection of things that the function actually hits. The codomain is the larger set in which the range lives. Okay? Yes, there's a question back here. Yeah, but we'll talk about range here in just a minute. So if f of a equals b, so if f of some input a is equal to b, then here's some more language. B is called the image of little a under f. Okay, so here's kind of a little picture of what's happening. I like to draw pictures, all right? So here's A, here's B. Okay, F is going from this set to that set. Okay, F takes us from the input set A to the output set B. And in particular here, we're saying if I take this element, little a, where does this guy go under F? This guy goes to little b, okay? So little f takes little a to little b, yeah? And b is called the image of a under f. You kind of see like, it looks like f sort of shooting a light ray, yes? F, if I kind of draw this picture, it looks like f is kind of shooting a light ray from a over to b, yes? So that's one reason why we call b the image of a under f, yeah? A is called the preimage of B. That kind of makes sense, right? So if I'm looking at this and I'm saying, okay, where does this thing come from? Where's an input that goes to this thing? Well, A would be that pre-image. Does that make sense? That means if I applied F to that input A, it would take me to B. This picture kind of makes sense. Okay, so we have domain, codomain, right? Domain, set of inputs, codomain, the place where the outputs live. Yeah. We have image and we have pre-image. These are kind of terms that we're going to be using. Any questions so far? Now, what's the range? Okay, so range of F is the set of all images of points in A under F. And it's denoted by F of A. Okay, so let's kind of draw that same picture again. I should have just left it on here for crying out loud. Okay, so here's F. Here's B. Okay, if I take anything from A, there's going to be some set that gets formed inside of B that we'll call F of A. So this guy, F of capital A, that is called the range. Okay, but what is B called? Yeah, B is called the codomain. Okay, so the range is the collection of all images of things in A. Does that make sense? So it's the set of all actual outputs, right? Range is set of all actual outputs. Okay, and you notate that by F of, and you put a capital A in there because you're thinking of taking the image of any possible input from A. And of course, A, this guy is called the domain. Okay, so once again, F of X equal to X squared. This is a function from the real numbers to the real numbers. Okay, so this guy is the domain. This guy is the codomain. But what is the range? What's the range of this function? Yeah, although it's a little tricky because I would have to include 0, yes? So I could just use interval notation. I could go 0 to infinity with 0 included. Does that make sense? And do this interval notation where I include 0 itself. And notice that the range, okay, let me just write it this way. The range is what's the, we've just learned some set theory notation and terminology. We would say that the range is related how to the codomain? It's a subset, yeah? So the range is a subset of the codomain. Yeah, the range is, you can kind of see that down here in this picture, right? You see that F of A is in Venn diagram form sitting right inside of B, the codomain, yeah? Is this making sense? So the range happens to be a subset of the codomain. Okay, continuing on. Two functions are equal if they have the same domain, and of course they have the same codomain, and each element of the domain is mapped. By the way, you often say map to talk about sort of moving from an input to an output. You use the word map. I remember I had a professor that started using that word just out of the blue, and I was like, what is he talking about, right? Map? That means something else in my mind. But in mathematics, when you say map, you're kind of talking about going from an input to an output. Does that make sense? A function maps an input point to an output point. That arrow kind of is showing us where it maps to. Does that make sense? Okay. So same codomain, same domain, and map each element of the domain to the same element of the codomain. I mean, come on. Obviously, that's what it means to be equal as functions, correct? Just everything has to basically be the same. Okay. Okay, let's use some of our logical notation. A function is 1-to-1. I can't emphasize enough how important this concept is. 1-to-1. If and only if, what does it mean to be 1-to-1? If and only if the output of two things are the same. Okay, that's what this is saying. It's saying that the image of A and B are the same. Yes? The image of both A and B are the same. So here, let me just draw a little picture, keeping track of what's going on here. Here's A. Here's B. Here's our function taking us from the one to the other, yes? And what this is saying is f of A is equal to f of B. So there's a couple of things. So this is supposed to be f of A, but it's also f of B. So apparently there are two things over here, A and B, that were mapped to this thing. Is it ever a problem for a function necessarily to send the same, or to send two different numbers to the same place? Can you think of a function that does that? Like that takes two different inputs to the same output. Can you think of a situation where that happens? Yeah. Well, x squared, the one we've been looking at, f of x equal to x squared, for instance, like so if f of x was x squared, then of course f of minus 1 is the same thing as what? Okay, do you guys see that? Okay. But, so it's possible to have two inputs go to the same output. Does that make sense? That's allowed. What's not allowed is for one input to multiply into multiple outputs. Does that make sense? So one input can never spontaneously generate itself into multiple outputs. That's what's not allowed for a function. But two inputs going to the same output, that's fine. Okay? But one-to-one is a special kind of situation. It says if you ever have the same image, then what's true about the inputs? If the images are the same, then inputs are the same, right? So what this is saying is images the same implies inputs the same. Okay, so the picture I drew up here is not an example of a one-to-one function. Okay, this function took two things to one thing, yes? In fact, f of x equal to x squared takes two things to one thing at times, yes? For instance, -1 and 1 as inputs get mapped to the single element 1, yeah? Okay? So one-to-one functions are special. They never allow for two inputs to go to the same place. You guys understand what I'm saying here? Yeah? One-to-one functions never allow two inputs to go to the same place. That's what is not permitted. Okay? So in other words, another way to say this, by the way, a logically equivalent way to say this would be to say that A different from B implies what? F of A is what? Different from f of b. That's the contrapositive of the other thing, yes? So if I have two different inputs, I better have two different outputs. But that's the same thing as the images being the same, forcing the inputs to be the same, yes? Okay, we're getting pretty sophisticated with our logic. So one-to-one, that means the same thing as injective or being an injection, okay? Those are all equivalent terms. Does that make sense? Okay, so I ask you, what test could we use from pre-calculus? Someone already mentioned the vertical line test. Horizontal line test. Horizontal line test. Okay? So yes, the so-called horizontal line test. Okay? Why? Well, okay, so for instance, if I'm looking at, not to just keep using the same stupid example over and over and over again, but this is f of x equal to x squared. If I apply the horizontal line test to this bad boy, notice that I hit it in two places right here, yeah? So drawing a horizontal line means a single output, yes? A horizontal line means this is a single output. But since I hit the graph in two places, that means there are two inputs, like right here and right here, that produce that same output. Does that make sense? So maybe this is like the number -1, and this is the number 1, and then this would be the output. What would that output be? 1, yes? Okay. So here I had two separate inputs giving the same output. Therefore, this function is one-to-one or not one-to-one? Not one-to-one. Okay, so passing the horizontal line test means any horizontal line had better only hit the graph in one place. Does that make sense? If the horizontal line ever hits the graph in more than one place, you know that you have multiple inputs going to the same output. Once again, if you ever have the horizontal line crossing your graph multiple times, that means that multiple inputs went to the same output. Yeah? Okay, so let me just say that this guy is not one-to-one. Okay? Not one-to-one. Does that make sense? One-to-one, injection, okay? Injective, those all mean the same thing when it comes to function terminology. Surjection. Okay? A function f from A to B is onto, or is surjective, or is a surjection. Hey, that's interesting, right? If you give me any, okay, so think about this. You hand me any element in the codomain. Remember, B is just the codomain, yes? Any element in the codomain has a corresponding input that hits it under F, yes? That's what this is saying. For anything in the codomain, there is something in the domain such that F sends A to B. Okay? So basically what a surjection amounts to, think about it. We had two concepts. We had range and we had codomain, right? What was generally true about how the range related to the codomain? Subset. What a surjection is it says it's not just a subset. It's actually what? Like the range is not just a subset, but it is equal to the codomain. Okay, so this is range. The range of the function equals the codomain. Okay? Range equals codomain. Does that make sense? Okay? So for instance, boy, I don't know, let me think here. F of x equal x squared. Okay? F of x equal to x squared, where f goes from the real numbers to the real numbers. Okay, so think about this. Here's the graph. Okay? What's the problem? What things are actually hit by this function? I like to think of the graph as kind of casting a shadow on the y-axis. Yes? And it looks to me like the range is just what? We already talked about this, but the range is 0 to infinity, which, by the way, is a strict subset. Okay, sometimes we say that, well, actually, we had a notation for that. You just didn't put the little equal sign on there, right? Is a strict subset of what? Of the real numbers. So is this a surjection? No. Right? So this guy is not onto. This is not onto. Okay? So again, it would be onto if you could give me anything in the codomain and I would be able to find something that goes to it. Yes? Yes. Yes, sir. Well, I mean, we don't have to actually talk about it that way. We could have actually, that's the thing that's kind of loosey-goosey here. The way we usually talk about the function f of x equal to x squared, we just generally think of the codomain as being all real numbers. But you're right, we could restrict our attention to just what? Right, positive numbers including 0. We could actually restrict our attention there, and then suddenly that function would become what? It would be a surjection. It would be a surjection onto the numbers from 0 to infinity. Yes, but I would have to change the typical codomain. Does that make sense? But would there really be a way to make this one-to-one? Think carefully. Would there be a way to make this one-to-one? Restrict the inputs. Yeah? So for instance, if I looked at f of x equal to x squared, it's a great question. F of x equal to x squared, where I thought of f as having domain 0 to infinity and range and codomain what? 0 to infinity. Then all of a sudden this graph would change, wouldn't it? It would go like this. Is that a one-to-one surjection? Yes. That would be a one-to-one surjection from 0 infinity to 0 infinity. Yes. It would pass the horizontal line test, and every single number would be hit in the codomain in that case. But there I had to kind of change my thinking a little bit. Yes. In fact, we do that sort of thing. I don't know if you remember this in calculus, but you do that sort of thing when you deal with inverse functions. Because in order to have an inverse function, you need to be able to kind of change from xy to yx. So instead of x being the input, y becomes the input. In order for that to happen, you'd better never have two things going to one thing. Okay? Because that would make one thing go to two things if you flip things around. Does that make sense? If two x's went to one y, then when I switch x and y in the inverse, what would happen? One y would go to two x's, which is not a function. Does that make sense? Flies in the face of being a function. What does this mean about the range and codomain? We already said that. What does it mean? They're equal. Bijections. Well, a bijection is simply a one-to-one correspondence is simply both one-to-one and onto. Yeah? So a bijection is something that's both one-to-one and onto. And by the way, you already read in the Heart of Mathematics a little bit about this, did you not? When we were talking about infinity, yes? I mean, they probably weren't talking about, it wasn't talked about in such formal terms here, but yeah. So how do I check if something is a bijection? Well, it would have to pass the horizontal line test, and the whole codomain would have to be reached. Okay, what that means is the range equals the codomain, yes? So you would check the horizontal line test, and you'd have to check that the range equals the codomain. By the way, I understand, we're still talking about this as if we're only talking about functions of real numbers, right? But that's the thing we know best, so that's why I keep going back to these examples to try to illustrate what we mean, okay? What about the function sine of x? Is the function sine of x, if I think of that function as going from the real numbers to the real numbers, is the function sine of x one-to-one? No, it's badly not one-to-one. It's many to one, yes? Okay, so for instance, I mean, if I drew a horizontal line, it's gonna pierce through that graph in an infinite number of places, yes? So long as that horizontal line is between -1 and 1, which brings me to my second point. Is that function onto the whole real line? No. The sine function is not capable of reaching any numbers outside of where? -1 to 1. Its range is -1 to 1. So it is not onto the whole real line, yeah? But it is onto the interval from -1 to 1, yeah? And to get something that's 1 to 1, I would have to restrict the domain of the sine function. You see what I mean? Okay. So how could I restrict it? I mean, you actually do this when you try to find the arc sine function, the inverse sine function. You restrict it from -90 degrees to 90 degrees. And that's as far as you can go. If you go any further, you're going to start repeating things. Yeah? So if you restrict the sine function in its domain to negative pi over 2 to pi over 2, you end up getting something that's 1 to 1. And it's also onto the interval from minus 1 to 1. And then you can start talking about an inverse function based on that, okay? Oh, as if I knew what the next slide was going to be, okay? Inverse functions. If f is a bijection, what does bijection mean again? Yeah, 1 to 1 and onto, right? It's an injection and a surjection, okay? Is a bijection from A to B, then the inverse of f, denoted by f with a little minus 1, okay, which not to be confused with 1 over f, yes? It's the inverse function, is the function from B to A that just does the exact opposite of what f did, okay? So for instance, let me just draw a little picture here. Here's A, here's B. F goes this way. Where does F inverse go? The other way. In fact, it does the exact opposite. Okay, so if this is X, okay, and this is Y, okay, F will take X to Y. So here's what F does. What does F inverse do? Yeah, it takes Y to X. Right, that's what F inverse does. There's lots of famous functions that are inverses of each other. E to the x, what's the inverse function of e to the x? Natural logarithm of x. Yeah? Okay. What is the inverse function of x squared? Square root. But there you would have to restrict your attention to only or 0 and up. Does that make sense? So that you have a 1 to 1 and onto function. That's why oops, this thing is flipping upside down on me here. So let me just draw this picture. So look, if I restrict my attention on f of x equal to x squared to just 0 to infinity in the input variable and 0 to infinity on the output variable, then what is the inverse function going to look like? Like this, right? Remember, you get it by sort of flipping across the line y equal to x. Why does that work? Well, flipping across the line y equal to x has the effect of swapping x and y values. Yes? It swaps the x and y values. So if x went to y under f, then y will go to x under f inverse. Okay, so this would be f inverse of x equal to the square root of x. Yes? Okay, so there's some inverses of each other. Is this making sense? Okay. What is a graph of a function? Well, it's the set of ordered pairs of inputs and outputs. Yes? So when you were graphing things in high school or junior high or whenever you started that journey of graphing functions, what you were doing was you were just graphing the collection of all inputs and outputs. Yes, as ordered pairs. The first member of the ordered pair was the input. The second member was the output. Yeah. So it's a set of all A comma B where B is actually realized as an image of some little a. Yes? Where B is actually realized as the image of little a. Okay? That's the key. Any questions on that? That's literally what a graph is. Okay? Here I wanted to be clever and actually think about the function x squared. I mean, why not? Let's just keep thinking about this function over and over and over again, right? F of x equal to x squared from z to z. Do you remember? Okay, what's z again? Integers. Okay, there's the integer graph of this thing. If I restrict my attention from input integers and output integers, this is what I would get. What is the domain? Okay, well, the domain is the collection of integers, apparently. What's the codomain? Integers. What is the range? Well, it's, you know, it's this set. Oh, actually, we actually have, ooh, let's see if you remember this. What is the name of the set that has, what's the name of the set that has 0 and all the positive things? Yeah. That was the natural numbers, right? 0, 1, 2, 3, etc. We agreed that in this class it will include the number 0, yes? So we already have a notation for the positive integers. It's just z with a little plus up there, yeah? All right. Is this function injective? No. Why not? Yeah. The horizontal line test, right? I mean, even this way, even though this graph is like discrete in this way, there's still horizontal lines that encounter multiple points, and therefore, you know, for instance, -1 and 1 as inputs go to the same output, 1. Yes. Okay. Is it a surjection? No. Is it a bijection? Well, clearly not. If it's not an injection and surjection, it's not a bijection. Yes. It has to be both of those things to be a bijection. Okay. I'm gonna skip this one because I think I basically already did it. It was the square root example. Okay. And we already talked about the sine function as well. I was just going to draw something and have us think about that, but I'm going to go ahead and move on. Last thing I want to talk about is composition. Okay. Composition. Now, you guys, if you've taken calculus, there's a lot of focus on composition of functions, plugging a function in a function, okay? And to find derivatives of functions in functions, what rule do you have to use? Chain rule. That deals with composition of functions. So composition of functions is a big deal, okay? So in this case, I've tried to draw a picture illustrating what's happening. You start with A on the left, and then you have B, and then you have C, correct? A is the domain of G, B is the codomain of G, but B is the domain of F, and C is the codomain of F. Does that make sense? Okay. And I can actually compose those things and kind of watch what happens as I do that. Yeah. So basically what I'm illustrating there is like A, little a, for instance, under G goes to G of A, which is an element of big B. And then I apply F to that because I can, okay? And F of G of A goes to something over in C, okay? And the way you notate that is it looks almost like fog. Do you see that? So it's in the way you say that is F composed with G, okay? So what that means is you almost read that thing right to left, like you're reading Hebrew or something. I don't know if you knew that, but you read Hebrew like right to left, okay? So you almost read that thing right to left. If I want to apply to that input X, what is going to get applied first? G will, and then what? And then F. Okay, so that's how function composition works. You kind of create like a little chain of functions and you compose them. That's why it's called composition. Okay? Does that kind of make sense, hopefully? Yeah? So like, for instance, what if I had, you know, let's see, G of X equal to 2X minus 1, and F of X was equal to the square root of X. Then what would F composed with G of X be? Yeah, like you would plug in G into the function F. So that would just be the square root of X replaced by 2X minus 1. Basically, everywhere you see X inside of F, you replace it with the entire function G. Yes? Okay, so that's how composition works. Okay? Cool. we're going to be talking about infinity quite a bit by using our newfangled kind of thinking in terms of sets and functions and whatnot. That is going to be coming very soon. That's it for now, though.